Hello, my name is Edward Derry and I am a second-year aerospace undergraduate student with the Georgia Institute of Technology working in AE 2610, the Introduction to Experimental Methods course. I'm here to present the combustion dynamics in a Rijke tube experiment. The left figure gives a general idea to what a Rijke tube is and what it does. A Rijke tube simply is a tube with two open ends with a source of heat, such as a flame, in it. Usually it's approximately a quarter of the length of the tube above the lower end. Above the flame, pressure fluctuations result in acoustic excitements and produce sound and pulses. The sound produced from inside the pipe is a self-amplifying standing acoustic wave with a wavelength twice the length of the tube. Simply put, a Rijke tube can take heat and generate sound from it. On the right is the configuration for this experiment. The lower end of the tube is open-ended, while the upper end is connected to an exhaust pipe in the ceiling with a decoupler, which acts as a muffler, simulating the other open end of a Rijke tube. The heat source is a propane-fired burner moved vertically by remote control inside the tube's lower end. This experiment was conducted to study and further understand the processes taking place in a Rijke tube, since pulsed combustion is known to have a higher intensity than steady combustion. The decoupler was just explained before as a muffler and connection to ceiling exhaust, but a simulated open end to the pipe. Piezoelectric transducers are acoustic pressure transducers fitted to the tube at three locations: the center of the tube and near the centers of the upper and lower ends of the tube. They are used to monitor pressure fluctuations by translating the pressure into proportional voltage. The photomultiplier, or optical detector, had instrumentation failure and was not included in this experiment. The rotimeter simply measures the fuel flow rate, and the pressure gauge measures the pressure in the flow meter. The oscilloscope and computer data acquisition system are for collecting data, but the oscilloscope was not used as gleaning accurate and precise information from it proved too difficult and unfruitful. The first run was performed with the flame at the 0-inch mark with the valve closed, and the second with the valve open. Run 3 moved the flame to the 2-inch mark and closed the valve again, and the fourth run was just raising the burner until there was no more resonance, and then collecting data from that point, which was 4.8 inches. Again, the valve was closed. Fifth run was just waiting to see at what point would resonance return, which came out to 1.2 inches, again under the same conditions. So now we go into our results. We'll start with frequency. As you can see, the estimated tube resonance frequency was 92.7 Hz, which we'll get into how we calculated that in a second. But I want to note that runs 1 and 3 and runs 2 and 4 had identical peak frequencies across all three transducers. This is going to come important into our analysis later. So now we look at the resonance frequency calculations. As we can see, we use frequency equals the speed of sound, which is A, divided by wavelength lambda. And we know in a Rijke tube that the wavelength is 2 times the length of the tube. So we get F equals A over 2L. And we know that A, the speed of sound in of a gas, is equal to the square root of the specific heat ratio, gamma, times R, the specific gas constant, times T, temperature. Since we're on Earth, we're using 287 for R. The other givens are on the second to last line, and L is experimentally measured in inches and then converted to meters, and we get 92.7 Hertz. We then move on to amplitudes, which was actually given to us in volts, if you remember from the transducers. So we have to do some math in order to get these decibel values. But I also want to note, again, runs 1 and 3 and 2 and 4, consistent with the frequencies, are equal or at least very close to each other, with standard deviations low compared to their mean. And their means, again, very close. How did we find the amplitude? Well, we got the root mean square voltage per transducer per run, multiplied it by 1,000 to get millivolts, and then put it to the test with a chart given to us in the lab manual. Extrapolating the slope from that chart, we were able to get, or that function from the chart, we were able to get that the pressure in psi is equal to dividing the millivolts by 97. So we get P. We divide P by 2.9 times 10 to the negative 9, which is just the human threshold for hearing, and plug it into the rest of this equation, and then we get the decibel values. Now, I know we didn't do the photomultiplier in this experiment, but we were given the data by the data acquisition system, so I thought I would do a quick analysis on it. The frequencies are all the frequencies are the same, and the root mean square millivolts are pretty much the same. Their mean value is 0.417 and millivolts, and the standard deviation is very small, 0.00870. So they're pretty close to the same. So then we look at the relative angles. We can see that we just subtract from each of the columns the value that's in P2, which was not originally 0, but it is now because we're looking at relative angles. So it helps us understand what's happening phase difference wise. Some quick concluding points. Resonance means instability, right, because of oscillations going on. So in order for the combustor to move forward, to move towards stability and less resonance, the pressure drops. There's little to no oscillation outside of resonance frequency due to destructive interference. And lastly, since runs 1 and 3 had resonance and the peak frequencies are higher, it's safe to say that a closed end means more resonance and oscillation. So that means we can also say runs 2 and 4 had less resonance and oscillation, which would mean that they were more stable, which means it's more optimal for combustion. Thanks for listening.